Continue the open book test on Unit 2.3 and 2.4. We were using the product rule, the chain rule, the quotient rule, but at this point we said we can use whichever method that seems to be the simplest, and so we're gonna distribute. We're going to factor and reduce. We're going to do things to simplify these in this section. To basically show that yes, there can be times that it's simpler to not use the chain rule or the product rule or the quotient rule, and then there's some times that just demands us to do that. All right. Well, we're going to look for factors. We actually know that x equals -3 would be a discontinuity, but we've learned before that discontinuities could be removable by factoring. Even if it was a discontinuity, we could still find the derivative of this using the difference quotient. So that doesn't mean that you can't find the derivative, but we do know how to remove discontinuities from factoring, and we know that could remove that denominator of x minus 3 if we can have a factor of that x plus 3 in the numerator. Well, we need to think then, what does x squared plus 5x plus 6 factor into? And let's just recall, we know the AC method of factoring that we teach here, but we also know that if the A is equal to 1, then we know that what goes in our parentheses is just an x here and an x here. And what we can think is, what do you multiply to get C equals 6 and add to get B is equal to 5? So what do you multiply to get 6 and add to get 5? We would say, well, to multiply and get 6, you could have a 1 and a 6 or a 2 and a 3. To add and get 5, you would have the 2 and the 3. So what do you multiply to get 6 and add to get 5? A 2 and a 3. And those go directly in here. So when A is equal to 1, factoring is a lot simpler. You just say, what can I multiply to get C and add to get B, and stick them in there directly. We see there then that the x plus 3's cancel, and so this simplifies into x plus 2. So we rewrote the h function. So now the derivative h prime is simply the derivative of this sum. The derivative of x is 1, and the derivative of that constant 2 is 0, so it goes out. So the derivative is simply 1. Now, can you logically think about that? Let's actually think, well, the derivative is 1. I thought the derivative was the equation for the slope of the tangent line at any point. That kind of sounds weird when you first think about the equation of the slope of the tangent line at any point being 1. But if we were to graph this, we would have a linear equation with a y-intercept of 2 and a slope of understood 1 over 1. And so if we went up 1 and right 1, we would have that. And what we would see then, okay, we have a line, and if I were to pick any point on that line, the tangent to the line would be the line itself. From any point on the line, the tangent is the line itself. So the tangent would have the same slope as the line itself, and the slope of the line itself is 1. So again, let's not forget that when we're finding the derivative, we're finding the equation for the slope of the tangent line at any point. And it's got to make sense in whatever application that we're in. Okay. Let's look at the next section. The next section says find an equation for the line tangent to the graph of the function at the given point. Now, remember that the derivative gives us what? The equation for the slope at a point. So, to find the equation of the tangent line, we need to find the slope of the tangent line. We have the point of tangency 2, 4, and with that point and slope, we can do what? We can plug into y minus y sub 1 is equal to slope times x minus x of 1. Now, we've already got the point of tangency to plug in. So we're already going to have this, y minus 4 equal whatever the slope we come up with, x minus 2. We need the slope of the tangent line at that point 2, 4. But to find the slope of the tangent line at that point, we need to get the equation for the slope of the tangent line at any point, and then plug the x of that point in. So to find the equation for the slope of the tangent line at any point, we take the derivative. And the derivative of x squared is exponent times coefficient. 2 times 1 is 2. Reduce the exponent by 1 to x. So the equation for the slope of the tangent line at any given point is 2x. We can take the x of my given point of tangency 2 and plug it in. So the slope of the tangent line at the point 2, 4 would be 2 times 2, which is 4. So my slope of my tangent line at the point 2, 4 is 4. I have that point 2, 4. If I plug the slope we calculated and place the slope in my formula, then I've got a 4 right there. Now I've got the equation of the tangent line at that point in point slope form. I want to transform it into slope intercept form. To do that, I'm going to distribute. I'm going to have y minus 4 equal 4x minus 8. And then undo the y sub 1 that was plugged in. And I'm going to have y is equal to 4x minus 4. So there's the equation in slope intercept form of the line that is tangent to y equal x squared at the point 2, 4. Okay? Let's graph that just to see what we have. I'm going to go to the graphing calculator. So I'm going to come in here and I'm going to plug in, well, let me clear this out. Clear my y equal. I'm going to go to y equal, it was x squared, right? Y equal x squared would be the graph of the original quadratic. Is that right? So there's the graph of my original quadratic. Got a few things that I should turn off here. Ignore those points. That's another application. We'll just leave that. And then we said, okay, we've got the equation, was it 4x minus 4? Yes. 4x minus 4 was the equation of the tangent line at that point. And we can see that that looks pretty good. Let me go to my window and let's move our x max out to about 4 and hit graph again just so we can get a little bit better look. So we can see it does appear to be a tangent line. It should hit at the point 2, 2. Let's just ask it where these two intersect. So we're going to go to second trace, which is calculate. We're going to ask it for number 5, the point of intersection. My first curve is the y1. My second curve is the y2. And I want to guess, so I'm going to get it pretty kind of close to the point of intersection and hit enter. And it validates, yes, those do intersect at the point 2, 4. You can see some decimals in there, but we realize that's some calculating problems. Anyway, so we can verify with the calculator that yes, we did find the line tangent to that point, to that curve at that point. All right. So again, it's good to visually remember what we're doing. Sometimes in math we go through processes and we forget what we have. What did we find when we did that? Okay. So let's go to number 11. Number 11, we have a point. We're wanting the equation. We need the slope of the line and a point on that line. And then we could plug in, we would have y minus the y of 35 is equal to the missing slope times x minus the x of 3. So we realize that what we need is the slope of the tangent to that curve at that point. Now, we can solve number 11 using the product rule, or we could distribute and come up with a polynomial, and we use the sum or difference rule. Let's go ahead, just for the sake of practice, and use the product rule here. Just to remind ourselves. So if we're going to do the product rule to get the derivative, the product rule is what? The first times the derivative of the second, which would be 3. And then what operation goes with the product rule? Plus sign. And then we would take the second, which is 3x minus 4, times the derivative of the first, which would be 2. So first times derivative of second plus second times derivative of first. We will distribute and then combine like terms. So we're going to have y prime is equal to 6x plus 3 plus 6x minus 8. After combining like terms, we'll have y prime is 12x minus 5. Any questions on that? Okay. So we want the slope at the point 335. So we're going to take the x of that point and plug it into our equation for slope. The derivative gives us the equation for the slope of the tangent line at any point. We plug in the x of the point 335. We're going to get 12 times 3 minus 5. So y prime is 36 minus 5. So y prime is 31. So the slope of the tangent line at that point is 31. We put that in our slope position in our point slope formula. And now we can change it from point slope form into slope intercept form. To do that, we will distribute. So we're going to have y minus 35 is equal to 31x minus 93. Undo subtraction by addition. We'll get y is equal to 31x, and then we're going to have minus 58. 58, thank you. Missed that one. Minus 58. So there's the equation in slope-intercept form of the line that is tangent to y equal 2x plus 3 in parentheses times 3x minus 4 in parentheses at the point 3, 5. Any questions on number 11? Okay, very good with that. All right. And then number 12, and number 12 we'll go ahead and use the quotient rule again. It's easily factorable. We could factor this into an x plus 3 times an x minus 3 because we have the difference between two squares, which would factor into those binomial conjugates. The result would be that those would cancel and you'd have x minus 3, and f prime of x would be equal to 1. All right. Now, let's go do it the hard way. That was the easy way. Because we just want to see the quotient rule one more time. And so let's remind ourselves of the quotient rule. We have f prime of x equal to use the quotient rule, you take the denominator. We always start with the denominator, and denominator appears 3 times. So denominator times
the derivative of the numerator.
Okay, so we got denominator times derivative of numerator, which would be 2x, and then
Minus the numerator.
a minus Okay, and then we're gonna have the numerator times derivative of the denominator, 1, all over
Denominator squared.
the denominator squared. Denominator squared. Okay, so we'll run through that again. We had denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. All right, now we'll gather like terms and all of that good stuff. So we're going to have f prime of x is, we can distribute here. We can distribute that negative there. And so we're going to have 2x squared plus 6x minus x squared plus 9 over x plus 3 squared. And then we're going to have f prime of x is equal to 2x squared minus x squared is x squared plus 6x plus 9 over x plus 3 quantity squared. Now, you may have recognized this as being a squared plus 2. Let me just write this out. As x squared plus 2 times 3x plus 3 squared. Did you notice that? X squared plus 2 times 3x plus 3 squared. That's a binomial square. And so we have a binomial square expansion. So you may have seen, that was interesting, or not seen, that is the question. No. You may have seen that this is like the binomial x plus 3 times itself. Would you recognize that as a perfect square trinomial? Okay. Remember, to be a perfect square trinomial, if 1/2 of b squared is c, then it's perfect square. Half of 6 is 3 squared is 9, so it's a perfect square trinomial. So it factors into x plus whatever half of that b term was, 3x plus 3 squared. So we have x plus 3 squared over x plus 3 squared. I can get on the things across correctly. Well, that's equal to 1, because anything divided by itself is 1. So we got that same 1 that we got while ago when we factored. It just took us a little longer to get there, and we still had to factor. But it was good to re-see the quotient rule. Okay, so we now have a point and the slope, and we can plug those into the point-slope formula. So we're going to have y minus the y of the point 4 is equal to the slope of 1 times x minus the x of the point 7. We're going to distribute here. So we're going to have y minus 4 is equal to x minus 7. Get the junk off of y, or remove that y sub 1 thing. And so we're going to have y is equal to x minus 3. So there is the equation for the line tangent to f of x equal x squared minus 9 over x plus 3 at the point 7,4. Any questions on number 12? All right. Well, that was the end of the open book test for 2324. Hope you do well on the test. Thank you.